what we're going to start out with, I think, to show the concept of normal forces and friction all in one, we'll look at an object that we're attempting to push across the floor. And if we look at that object, then we've got a number of forces acting on it. And when we're enumerating forces acting on an object, right, we're looking for anything that's in contact with it that can apply force. And then we have our one force at a distance, which is the force of gravity. So if we have an object that's just in free fall, well, then there wouldn't be any contact forces and we just have the force of gravity. But now that we're in contact with the ground or the floor, then we can have first the force of say us trying to push this thing along, and we'll call that F of P, for person or push or something like that. And we'll put a number to it. We'll say 160 newtons, which is like 35 pounds of force or something like that. So pretty decent push. And it's in contact with the floor. And if you haven't seen the normal forces video that I recorded before, you should maybe check that out for some more detail on normal forces. But they're called normal forces because they are always perpendicular to the two surfaces that are in contact that's causing that force, okay? And then of course we have our force at a distance, which is gravity downward, so F sub G. And the other force that's going to be acting in a situation like this, where we're pushing a box of books or something like that across the floor, is the force of friction. And the force of friction is always going to resist either the attempt to push it, if we're staying stationary like you're pushing but not able to actually dislodge this object from being at rest, or it's resisting the motion of the object if we're in the so-called kinetic friction. Since we don't really know much about the situation yet, we'll just call it F sub F, and we'll put it in opposition to the push that we're putting on it. Okay? And I've drawn it a little smaller, but we don't actually know that at this point. We'll just be able to figure it out as we go through this problem. So, say that this object is at rest, to start with at least, okay? And we give it this push of 160 newtons of force. And we've done the first step in any force problem, which is to draw ourselves a nice diagram of all of the forces acting on that object. And the question is, does it move? Now, if you were just given this picture and you were told all the forces were proportional to their length, right, which you're usually supposed to put in if you know what the magnitudes of all the forces are, we would say, oh, well, F sub P is a longer arrow than F sub F, and so it should start accelerating to the right. However, what we've got here is a situation where we don't know all of the magnitudes yet, and so we can't make that assumption, and we need to figure out whether or not this thing is moving. Well, we say it's at rest to start. We start pushing on it, and so the question essentially translates to, in physics terms, is F sub P greater than F sub F static? And static friction is the kind of friction that resists the attempt to move an object, right? So an object's sitting there, you try to push on it, static friction resists that. And it'll keep resisting that until you manage to exceed its largest value. And the largest value that static friction can ever achieve is mu s F sub n. Okay, so this is what our question then becomes in more physicsy terms. Okay, so F static max is equal to mu s F sub n. Now, a couple of things there. If you haven't seen the video on friction, then maybe this looks unfamiliar. So that this is corresponding to that. This mu s is the coefficient of static friction. And it's just a number. You notice that it has to be unitless because we've got forces over here and we've got forces over here. And it has everything to do with essentially how slippy the surfaces are that are in contact. If they're very slippery, so like you have you know, ice with a little bit of a sheen of water on it or something like that, like you would if you were ice skating over it, then you would expect a very low coefficient of static friction. And if you had like rubber on concrete, like a car tire or something like that, that tends to be quite sticky. It doesn't slip much at all. And so you would have a high coefficient of static friction in that case. But it's really just showing you the proportionality between the force of static friction in this case and the normal force acting on that object as a result of those surfaces, in this case the floor and whatever this box is, you know, being in contact. Okay, so this is the question that we're trying to answer, and we can answer that because we know some things. Okay, now we would have to look up whatever mu s is. So let's say mu s be 0.5 for, say, like a cardboard box, so cardboard on a wooden floor. Seems reasonable. And let's say that the mass of this box is 30 kilograms. Okay, we would need to know that at least. Okay, let's figure this out. So we want to know what this maximum static friction force is. If we figure this out, then we can know whether or not it's less than or greater than or equal to this 160 newtons. And if our 160 Newton push is bigger than the maximum static friction force, then we know that this object is going to break away from being at rest and start accelerating. Now, we know what this is, right? We just talked about that. And we need to figure out what the normal force is. However, in this case, that's a really simple thing. And the way we're going to do it is we're going to look at our free body diagram. We're going to say, well, this object is not going to be accelerating vertically, right? We're not burrowing down into the floor. We're not levitating up off of it. There's no reason why that would ever happen. We don't see that happen spontaneously. So we know that all of the forces in the vertical axis have to cancel out. And the way that you might write that out, if you were doing it carefully, is to say, okay, well, the force, sum of all the forces in the y direction. So if we have y vertical, x horizontal, like we usually do, then we've got F sub n up, and we've got F sub g down, and it's not accelerating vertically, so that all has to equal 0. And so the magnitude of F sub n has to be equal to the magnitude of F sub g. And we know what F sub g is, right? If you go back to the lecture where you're reading and you were looking, when we were talking about the difference between mass and weight, we know that near the Earth's surface, you can just write down that the force of gravity on an object is that object's mass times gravity, that gravitational acceleration, so 9.8 meters per second squared. So wherever we see an F sub n in this problem, we can substitute an mg. And so we come over here, we do that exact thing to find what this maximum static friction force is. And so we've got the coefficient, we've got the 30 kilogram mass, and we've got the gravitational, pardon me, that's me angling the pencil here so that I guess thinks I'm like it's drawing with a marker or something. Anyway, so product of all of those things should equal, I think, 147 newtons. You can check me, okay? 147 newtons. That's the maximum static friction force that can be supplied based on what we know about this situation. And we note that that is less than the push. And so the answer to this question, does it move, is yes. Yes, it does. Okay. We have 13 more newtons of force from our push. than we actually need to get it to break away and start moving. Okay? All right, let's answer one more question about this, and that'll just get us used to looking at this stuff and working with it. We're going to answer the question, so part B, say, of this question is going to be, how quickly does it accelerate? And for an instant, you know, when we're at still stationary, when we haven't quite started moving yet, but it's breaking away, then maybe the force, and thus the net force, and thus the acceleration of this object would be dictated by this maximum static friction. But as soon as it starts breaking away and having any sort of velocity, well, now you don't talk about static friction, you talk about kinetic friction. And the kinetic friction has an expression that looks a lot like the one for static friction. If you've seen the friction lecture, then you've seen this before. But if you haven't, here it is. Okay, so F sub k is equal to the coefficient of kinetic friction times F sub n acting on an object. Okay, so that again is going to be resisting the motion of the object. So as the object sort of accelerates this way, okay, in response to the push, that means that it's going to gain velocity in that direction. That means that the force of kinetic friction would oppose the motion. Now, we do need one extra piece of information if we're going to solve this problem. We need this mu sub k, which again is dependent on just the materials that are in contact, how rough they are, what they're made out of, all that kind of stuff. And let's say that it's 0.3, because coefficients of kinetic friction, though they might be close to the static coefficients of friction, they are always less by at least a little bit. So in this case, let's say that the coefficient of kinetic friction between a cardboard box and a wooden floor is 0.3. Okay, once we know that, we want to know how quickly is it accelerating, and it's accelerating in the x direction, right? There's still no vertical acceleration because, again, the box doesn't spontaneously levitate off the ground, okay? Or burrow down into it, I suppose. So we can look at the sum of all the forces in the x direction. We know from Newton's second law that's going to be equal to ma, and I put a little x to represent that it's in the horizontal direction. And there are two forces acting in the horizontal direction, right? If we look at our diagram, we've got F sub P in the positive direction, and we've got F sub F. I'll change that label to F sub K because we know it's the kinetic friction acting in the opposite direction, hence the minus sign. Okay, so we know the force of the push already. We are assuming we're maintaining our 160 Newton push on this object. And all we need to do is figure out what F sub k is, and then we can calculate what we want, this acceleration. So let's make some substitutions. I'll just leave that as F sub p, but we know it's 160 Newtons. We've got mu sub k, we've got F sub n. And F sub n, well, the situation in the vertical, right, this that we sketched out earlier, hasn't changed, right? Now this thing is moving, but there's still a force from the floor holding up the box against gravity, and gravity is pulling straight down. So we can rewrite F sub n again. Let's see if I have space down here, as just equal to mg in terms of its magnitude. So let's bring this up here. Give ourselves a little line to separate our work from part A. And if we want to know what a sub x is, then we just divide both sides by m. And then we just substitute in all of our numbers. Now, all the numbers are going to take up a lot of space, so I'm going to just point them out for us here. F sub p is 160 newtons. Mu sub k is 0.3. Mass is still the same object, so 30 kilograms. And g is just our 9.8 meters per second squared. Perfect. So you type all that into your calculator, and you should find that your acceleration in this case is pretty significant. You're really apparently giving this, this box of books or something a pretty good shove. And so the acceleration is going to be 2.4 meters per second squared to the right, so in the direction of your push. Okay, and there's the answer to part B of this little problem that we're trying here. Okay, so let me check on a couple of things. We've got, well, we briefly had a second person, okay? But any questions at this point? I suppose, Seamus, if your microphone still isn't working, then you can't ask them verbally, but you're welcome to type anything you like into chat. And of course, I'm recording this, so it should be available once I get a chance to download it and edit it up a little bit. Okay, maybe we should look at at least one more, maybe a slightly more complicated situation. And then if we have time, or if I have the inclination, depending on how many other people are here, we can take a look at a tension problem. And if we don't get to that today, that's all right. We'll maybe discuss it on Thursday for the class where we'll have a bigger group. Okay. All right. So I think I can preserve this if we ever wanted to come back to it, at least during this session. So I will add a page to my whiteboard. And what we're going to do is we're just going to complicate the situation a little bit. We're going to take essentially the same object. I'm going to put it on the same floor. And so we still have, you know, mu k is equal to 0.3. And we still have the mass of the object is 30 kilograms. And we still have a push that is 160 newtons. However, I'm going to change a little bit about that situation. I'm going to say that the force of the push, maybe you're quite a bit taller than this object, and so you're sort of pushing down at an angle, if you imagine your arms in line with that blue arrow. And that is going to be our F sub P. And that's still going to be 160 newtons in magnitude. But now it's tilted relative to the horizontal by, let's say, 40 degrees. Okay. And then the rest of the forces, right, we're still in contact with the same thing. So we're going to enumerate the same set of forces. We have our one force at a distance. We have a normal force from the floor acting on the object. And we have some force of friction here opposing that motion. And because we're just gonna sort of redo part B of the last problem, I'm gonna assume that we're in motion here. So we're sort of in the kinetic case. And so how about I actually relabel F sub F here to be F sub K, to specifically call out the fact that it's kinetic friction, okay? Now, the question again is how quickly does it accelerate? And so we're looking at the case where we've just broken away and started moving, so we're in the kinetic friction case, okay? You can use the equation for kinetic friction and the coefficient of kinetic friction. And we're going to figure out basically the same thing as part B on the last question, except that we've got the force of the push angled in this way. And that does complicate things significantly. And I wanted to do this not just to like do more math, but to illustrate a couple of things. Because one thing that students often get firmly in their head when they're seeing sort of the introductory simpler problems in forces is to automatically say, aha, normal force and gravitational force are going to be equal and opposite. And they're always going to be equal and opposite. And so wherever they see an F sub n, normal force, people will just stick an mg in there. And that would be a sweet shortcut if it was always the case. But as we've already talked about in class with that one conceptual question where, like, imagine if we push down on this object. Well, now there's two downward forces, gravity and your push. And so normal force, if you're not shoving the box literally through the floor or something like that, normal force is going to be larger to cancel out both of those downward forces and keep the vertical acceleration being 0. And we have a sort of situation like that here. And so these two forces, that normal force and gravity, are not going to be equal to one another in this situation. Okay, so let's take a look at it. Let's get some color in here. We'll go in green. And in this problem, now that we've sort of set up, we've got our knowns, we've got our force diagram over here. If we want to know the acceleration in the horizontal direction, because that's the only direction it can accelerate here, well, again, we want to write down the sum of the forces in the x direction is equal to the mass of the object times the acceleration of the object along that axis, right? F equals ma, albeit just for the x-axis. And you can write down the same thing for the y-axis, except we know that as long as the floor stays intact, that the acceleration in the vertical direction is going to be 0. And remember, this is y and this is x. Okay. So with any problem in physics, it's always best to maybe go straight at it and see how far you get. So we're looking for a sub x. So we can just start writing down all of the forces that have x components. And there are 2, right? There's going to be this little piece of f sub p right there. And we'll call that f sub p x. And of course, there'll be a y component as well. We'll call that f sub p y. Okay, but for this sum of forces, we'll have f sub p x acting in the positive direction, and we'll have the force of kinetic friction opposing that. And we can make some further substitutions, right? If we want to find the magnitude of that x component of the push, well, then we need to take the magnitude of the whole vector, that 160 newtons, multiply it by cosine of 40 degrees, and get that x component. Now, and then of course we can substitute the definition of kinetic friction, which is just mu k times f sub n. If we look at that equation, well, there's a lot in there, but we know a few of these things, right? We know the mass, we know the force of U pushing on it, 160 newtons. We of course know what cosine 40 degrees is, or can ask our calculators, and we know the coefficient of kinetic friction. But we still have 2 unknowns. We have the one that we're looking for, and we have f sub n, which we don't know off the top of our heads. F sub n, again, we want to look at the vertical forces. And the reason we want to do that is because F sub n is a vertical force in this problem. And so we can write out that 0 is going to be equal to F sub n up, F sub g down, so the minus sign, and the y component of the push also down, right? This guy right here, okay? And if we, let's give myself a little bit more space when we move down here. We've got F sub n is equal to F sub g, which is mg, plus F sub p, not cosine of 40 degrees, but sine of 40 degrees, right? So the forces that we had and here. And we just moved F sub n, well, moved them to the opposite side from F sub n in our equation. We know all of those things, right? We know mass, we know what g is, just a constant. We know what this is, and of course we can calculate that. So we can get that number. We can substitute it in up here for F sub n. We can divide everything by m, okay, to get acceleration by itself. And if you go through all of the plugging of numbers, and it might look a little bit intimidating, but it really doesn't take that long, you should get about 0.12 meters per second squared. So F sub n comes out to be just under 400, something like this. I'm keeping some extra precision because we're not quite to a final answer when we're at this point in calculating normal force. But you take that, you plug it back in, you put in all of your numbers, and if I've plugged them into my calculator correctly, then you get that the acceleration of the box is considerably less. And that makes sense, right? Only a component of our push now is acting in the horizontal direction. So even though everything else is equal, we're not expecting the acceleration to be as big as in the last one, which it was already all the way up at 2.4 meters per second squared. Yeah. So the other thing that is going on here, in addition to there just being like a piece of the force acting in the x direction, that F sub px, is that because we're pressing down with this y component of our push, well, that makes F sub n bigger than it was in the last slide by a significant amount, okay, if you go back and compare those numbers. And that means that the kinetic friction force, even though it's the same surfaces in the same object, F sub n is bigger, and so this term is considerably bigger, and so it cancels more of your horizontal push in this case. So your acceleration is relatively tiny compared to the last case, okay? So we're at about 10 o'clock. Let me see here. We've got Seamus, okay, and no one else. I'll probably chop this up. Not much of a video editor, but I'll probably chop this up into more digestible little bits. So these are like one problem and then this problem. And because it's only 10:01, and I'm sorry about your microphone issues, Seamus. It's told me a couple of times you can't actually hear me because you haven't connected to audio, but maybe that's been resolved and you can. I hope you can. In any case, let's take a look at one more example to do with tension. I've recorded the tension lecture stuff, like the sort of basic intro to it. Okay. And but I haven't managed to get it up onto YouTube and Brightspace quite yet, but that'll happen later today. And so let's take a look at an example that that should illustrate a couple of things. All right, and we'll add a third page to our whiteboard here. And let's say we've got, some support here. Could be the ceiling, could be, part of a building, whatever it is, stationary, immovable. And we take a piece of rope and we hang one object from there, block of concrete or something. And then we take another piece of rope and we attach it to this first object, and we attach it to some larger, block of concrete or box of whatever. Okay, it doesn't really matter for this example what it is. So we've got two lengths of rope here and here, and we've got two objects. And the first thing that we want to do is take a look at the free body diagram. That if this was a concept question, we were answering it sort of live, then what we would have is, please draw a free body diagram. Indeed. Please draw a free body diagram of both objects, okay? So that's what we're gonna do. And let's go down here with this one. And let's think about all of the things acting on this object. So we've got two things touching it. This rope up here, I'll just call it like rope A, and this rope down here. Now, if we just think about that for a moment, I mean, rope A is the reason why one doesn't fall, right? So that must be supplying the necessary upward force of tension. It's the tension in that piece of rope that is the force acting on this thing, okay? And that tension, by the way, acts equally sort of down on the thing that we've attached it to. So this tension here and this tension here would have to be equal and opposite, sort of pulls the same on both sides of the rope. And but that's not all that's acting on the first object, right? So we have F sub t. Let me actually call it F sub A, just to differentiate it from the other tension, because it has another chunk of rope attached to it, right? So we'll call it yeah, let's call it A, but this is a tension from the rope. And then, of course, there's a force of gravity acting downward on this thing. I'll call it G1 because we're talking about object 1. And there's also, because of the presence of this second object, we have another tension force from that rope B acting down, okay, pulling down on the first object. And because this thing is just hanging there, we're assuming that the ropes are remaining intact in this case, all of these forces should roughly cancel each other out. And that's why I was adjusting the length of these arrows as I went. Now, if we went ahead and made a free body diagram of the second object, you do that. Not a particularly good facsimile, but you get the idea. We've got just one thing pulling on it, and that's this tension in rope B. And it has to be, by the rules of tension, okay, has to be equal and opposite to the pull down on the other end of the rope. So I'll try to draw that reasonably accurately. Okay, so about the same length as this one over here. And we'll call that F sub B. I guess technically we should call it like minus B because it is opposite direction. And then the only other thing that can be acting on number 2, because the rope is the only thing touching the object, so there's only one contact force, is the force of gravity on that second object. Now I've drawn it like a little bit longer because it's a larger object. Assuming it's made out of the same stuff as one, it should weigh more. Okay, and again, it's at rest, so it's not accelerating, so these two forces I've drawn to roughly cancel out. So that's what your free body diagrams would look like. Now, from this point, you could be asked a whole number of things. If you were given, you know, say the masses of these two objects, you could figure out exactly what the tensions were in each one of these ropes. And if you knew sort of the maximum stress or tension that one of these ropes could take, you could figure out whether you would expect it to snap, that kind of stuff. But let's just show something that actually you can kind of intuit your way to, but you can also look at the free body diagrams and know what it has to be. So let's answer the question, how does the weight of the blocks relate to the tension here? So how does F sub A relate to the weight of these two things? So in other words, FG1 and FG2. Now, if you think about that, you're thinking, well, I mean, it must, since this rope right here is responsible for holding up both of those things, right? If you cut it, they would both fall. Then what you would expect is that the tension in that rope is just going to be equal to the sum of these two weights. Great. Okay. Let's see how that actually comes out of what we've just laid out for the free body diagrams of these things. So if we first look at the first free body diagram, so number 1, we know from looking at object number 1 that FA, that tension in the upper rope, has to be equal to the two downward forces, right? Assuming that nothing snaps and starts plummeting to the ground. Right, the magnitudes of this sum has to be equal to that one so that the acceleration of this object is 0. Okay, well, that doesn't quite get us to this. But if we then look at number 2, we notice that, well, this F sub B, the magnitude of that upward tension in that second piece of line, has to be equal to the weight of that second object. If it wasn't, right, it would be accelerating in some direction, but we're told it's just hanging there. So wherever we see an F sub B, we can substitute an F sub G1. And if we go ahead and do that right here, then we recover this expression, okay? So we can get that out of sort of the mechanics of the situation, looking at the physics of it and the forces acting and what must be equal to what. Or you can, in this case, rely upon intuition. But as we've probably found out in physics thus far, some of it is intuitive, right? You expect to get a certain thing, something should be bigger or smaller or the same, and you're right. And then in other situations, you're like, well, this seems like it should be the same. And physics tells you, yeah, actually, that's not quite how the world works. Okay. So we'll start with this simple conceptual example. We'll leave it there for now. And yeah, we'll come back on Thursday and we'll get the whole group together and we'll look at a bunch of concept questions to do with friction and tension and normal forces and all of that kind of stuff. And in the meantime, you can look for these recorded videos as well as a couple of other things to be popping up on the Brightspace page. Don't forget your assignments due Wednesday evening, and I will stop the recording.